I wish she could have learned to let things go. The E2 mechanism is the bimolecular counterpart to the E1 mechanism. Like the pair of substitution reactions, the two elimination reactions make similar products through different mechanisms. Following the naming convention, E2 stands for elimination bimolecular. Like its bimolecular brethren, E2's rate equation depends on two molecules, the substrate and the base. The mechanism is simple for this one-step reaction. There is a proton transfer from substrate to base and the elimination of the leaving group. These occur in concert with each other in one step. Key players in the E2 mechanism are the substrate, the leaving group, and the base. The substrate is an organic molecule with a leaving group and an adjacent proton. The carbon that bears the leaving group is the alpha position, and adjacent carbons with a hydrogen are beta positions. In an elimination reaction, these are removed from a substrate facilitated by a base. A double bond takes the place of the missing groups, resulting in an alkene product. Stereochemically, for an elimination to occur, the leaving group and acidic hydrogen must be anti-periplanar to each other. The alkene product will have a configuration in the likeness of the anti-periplanar rotamer of the substrate. The double bond can form between any alpha and beta positions. Regiochemistry describes where the double bond is more likely to form. Elimination reactions tend to follow Zaitsev's rule. More substituted alkenes are preferred and tend to be the major product. The most substituted product is called the Zaitsev product, and the least substituted product is the Hofmann product. The substrate is not the only reagent that gets a vote as to how the reaction proceeds. Steric hindrance will get in the way of the Zaitsev product. A large, bulky base, such as potassium terbutoxide, diisopropylamide, or triethylamine, will have trouble accessing more interior protons. These large bases will deprotonate beta sites more easily reached from the outside, which favors Hofmann products over Zaitsev products. The base can even prevent an elimination from occurring at all. Bases that also act as nucleophiles can result in some SN2 competition. The E2 reaction, like E1, removes a leaving group and a proton from a substrate, leaving a double bond in their place. Unlike E1, this occurs in one concerted step. Regiochemistry is important for determining what products can form from a given reaction. There are often multiple products, but can be influenced by the base involved. Sterically hindered bases will prefer the Hofmann product over the Zaitsev product. Though this reaction gives multiple products, the products are governed by a hierarchy that can be controlled. Impurities are still a consideration, but mitigated to a minor product. When you need an alkene in a major way, this self-destructive pair will get the job done. Thank you very much for watching, and join us next time when we set our sights on a rule of elimination reactions.